Thank you very much, Johnny, and I'm the organizers. Great to be back here at Lumini and have this chance to talk about my favorite problem, the isoperimetric problem with density. So a density is just a positive continuous function on the space. I call it here psi of x, which weights volume and perimeter the same. So weighted volume is just psi times unweighted volume. Weighted perimeter is just psi times unweighted perimeter. So this is actually completely different and simpler than a conformal change of metric. You know, when you multiply length by some factor lambda, you multiply area by lambda squared, and you multiply volume by lambda cubed. Here, everything just gets multiplied by this same factor psi. We all see this when we teach in calculus areas of revolution. Here in my calculus book, you see the formula for an area of revolution. Area equals the integral of the circumference of revolution, 2 pi x, over the generating curve. Or similarly, a volume of revolution is the integral of that same factor, that same density, 2 pi x, over the generating region. So when you're studying in calculus, R3 modulo rotations around the z-axis, you're really just studying the plane with density 2 pi x, or half plane maybe. And similarly, if you take any manifold and mod out by a group of isometries, then you get a space that has some density. But density comes up all over the place now. I was trying to keep on my blog a list of papers on the subject. There have been over 40 this year already. I can hardly keep up with it all. So why is this, I wondered? Well, I went to this big conference in Montreal, and I asked the young experts there why density is so important. And this is what Robert McCann had to say.
I guess manifolds with density can arise as limits of manifolds with volume, in which some dimensions collapse, and you get an accumulation of mass in those areas where you have collapse. They also give a nice model for other manifolds. For example, you can put Gauss measure on the Euclidean line, and it behaves in many ways like a positively curved manifold, like a sphere.
Gauss density example, and Emmanuel Millman.
I was thinking about why manifolds of density are interesting. So they're interesting because they appear as natural closure of usual manifolds under measure projection.
Projection.
So for example, the Gaussian is well known to be the projection of a high-dimensional sphere. And of course, you want to include the Gaussian measure in anything you study.
So even if you don't like densities, they're going to come up. You start with regular manifolds. Maybe you take limits or you take projections. You're going to get spaces with density automatically. And they both mentioned the most important example, Gaussian density. So Gauss space, GM I call it, is just Euclidean space, RM, with this Gaussian density that you're so familiar with, which drops off like e to the minus r squared over 2 in distance from the origin r. So it's very concentrated about the origin, and then the space becomes very rarefied as you move away from the origin. Not much perimeter and volume out here. All the perimeter and volume is rotationally symmetrically centered about the origin there. And there's that funny factor in front. That's just to make the total volume of the space, the total weighted volume, 1, which is very nice, very convenient, and much more sensible than the silly Euclidean space with infinite volume. What does that mean? Gauss space actually, in the category of manifolds with density, becomes the model space to compare every other manifold with density to. It displaces, dethrones the sphere as the most important example. Most important example is Gauss space. But I'm not going to talk a lot about that today. I want to talk about the isoperimetric problem in a space like Gauss space. So it's the similar thing, only now we have weighted volume and weighted perimeter. We're given some weighted volume, quantity, number, and we want to find the shape that minimizes weighted perimeter. And so for Gauss space, of course, there's so much symmetry, you might guess that it's just the ball about the origin. It's not. It's actually The only thing that would be nicer, a hyperplane. Through the origin, if you want to cut the unit volume in half, and displaced from the origin, if you want to enclose a smaller volume. Not unique, of course, because as you rotate, the plane could be at any angle, could be horizontal, could be vertical. There's that continuum of possible solutions to the isoperimetric problem with lots of applications. But one of the lessons that we learn from this is that the surface likes to go off to infinity. It still has finite volume or finite area because the density drops off exponentially. So it's a sensible thing to do. And it actually likes to go out there where the density is small. This is a principle. Isoperimetric regions prefer low density. And so when we have a density like the Gaussian density that drops off to 0 at infinity, they're going to want to run out to infinity. So I wanted, back in 2006, I asked my students to look at the simplest density I could think of, which grows at infinity. And the simplest case I could think of was just powers of distance from the origin. Positive powers of distance from the origin, r to the p. And now remember, isoperimetric regions prefer low density. So now, with more confidence, they made the conjecture that the solution should be in the plane a circle about the origin. Again, false. In fact, circles about the origin are not even stable for this problem. And I thought there was no hope of finding exactly what the solution was in this case. It doesn't go off to infinity. That would be way too expensive. It has to hang around the origin. It's not a circle about the origin. Didn't think anyone would find it, but 2 years later, my students found the solution, and it is a shape you've heard of. Anybody who doesn't know want to guess what this could be? It's not a circle about the origin. It doesn't have the rotational symmetry. You've all heard of this shape, I'm sure. The answer is a circle through the origin. Seems very strange at first. It doesn't even look like, oh, there it is, circle through the origin. It doesn't even look like it would be in equilibrium, right? Because it's in equilibrium for this density 1, and now we have this density that's changing as you move radially. Why would that even have first variations here? Well, you can compute it does, and moreover, it is the minimizer, not unique. You can rotate it around the origin and get a whole continuum of solutions to the problem. Amazingly enough, it's the same answer for every positive p. You still get the same family of solutions. There it is, a circle through the origin. On reflection, you realize it does have a certain symmetry to the similarity to the Gauss case, right? Remember, in the Gauss plane, the answer was a line, which is a circle through infinity, where the density is 0. And here again, we get a circle that goes through the point where the density is 0, which makes some sense because it's the perimeter that we want to make small. So the perimeter is most eager to go through the place where the density is 0. So maybe we could have guessed something like that. I would never have guessed something like that. The students then left it as a conjecture in higher dimensions that the solution for that same density, r to the p, would be a sphere through the origin. So the next summer, I took my students to the World Center for problems like this, that's Granada, and they looked at the same density, positive powers of r, but now not in the whole plane, just in that red sector, with free boundary along those rays that constitute the sides of the sector. And then ask what the isoperimetric solution is. So this time, maybe you're ready to finally guess. We shouldn't have given up yet. Indeed, now, it is a circle centered at the origin, finally. Circular arc centered at the origin, at least for small angles. Although once the angle gets large enough, it looks like the whole plane case, and it's a circle or semicircle in this case, through the origin. So you get these two different kinds of solutions. And what do you think? Do you think it jumps from one to the other? Or do you think there's a smooth transition from the circle centered at the origin to the circle through the origin? How many people, so we'll have a little vote here. That's how we determine things these days in the world. So how many people would say jumps from one to the other? How many people would say smooth transition? All right, so it's a large majority for jumps from one to the other. But as is often the case in the world these days, the majority is wrong. And there's this brief intermediate stage where you get what we call these undulatory shapes. And this happens when p equals 1, just before 3 pi over 4. So here you see some pictures. You see as you're getting up near 3 pi over 4, you still have the circular arc centered at the origin. And then about 8 degrees before 3 pi over 4, you go into this transition which lasts until at 3 pi over 4 you get down to the semicircle. One of the students made a little movie of this for you. Here you can see how it starts out. It'll be a rapid transition starting 8 degrees before 3 pi over 4 down to the semicircle. So it is smooth, it turns out. There is a smooth transition. And they proved most of the facts about this. They proved that it's the circle about the origin for theta small, semicircle for theta large, and this undulatory in between. The only thing that they couldn't prove were the exact transition points. Oh yeah, question back there. Yeah, good. Pedro.
Saying that it's exactly a circle, an arc of a circle.
Yes.
Point, then it stops being the arc of a circle, and then it goes back to being the arc of a circle.
Yes, although the two circles at the beginning and the end are centered at different places.
Yeah, but so that means that there's some.
It's not completely smooth, that's right.
Yeah, at some point.
Yeah, it's maybe C1 but not C2, the family. Yeah, kind of strange. Kind of strange, but it is a continuous transition. And they couldn't prove exactly when the transition starts and ends. Their conjecture was that the circles are minimizing as long as they're stable. It's often a conjecture. And all the numerical studies that they did in the picture I just showed you confirmed that precisely as far as they could compute, although sometimes the numerical estimates were hard to do. I asked them if there was anything they wanted to tell you about this, and there are the four guys. This is what Alexander had to say about it.
First, minimize our arcs, then come the undulates, then the semicircle forever.
We'd hope that circles around the origin would be isoperimetric as long as they were stable, and that's exactly what the numerical evidence suggests.
We have this numerical evidence that predicts these transitions, and we've proven that the transition exists for some period between the quarter circle and the semicircle. But the detail of the numerical approximations gets very, very bad around the semicircle. We used to think that the semicircle was minimizing starting exactly at pi, so in the half plane. But now we're not so sure. Now we think maybe earlier.
We've got the equations for height and curvature, but we can't show the period is increasing.
And then Alexander summed up the summer like this.
También descubrimos la combinación perfecta, problemas isoperimétricos, Granada y nosotros.
Now this interesting question about whether the circle is minimizing as long as it's stable can be written in analytic terms. So it's equivalent to this certain one-parameter family of analytic inequalities in polar coordinates. So here r is a function of alpha. And on the left-hand side, q is a parameter going from 1 to 2. On the left-hand side, you have the LQ norm of this function. And on the right-hand side, something a bit more complicated that also involves the derivative of the function, r dot. You can see when q is 1, the difficult part on the right goes away. You have the square root of r squared, which is just r, which is exactly what you have on the left. r the q is just r when q is 1. So it's trivially true when q is 1. And at the other extreme, when q is 2, it turns out to be essentially equivalent to the standard isoperimetric inequality in the plane, just for density 1. And so you might think you could get this by some kind of interpolation argument. That's what we were hoping. We couldn't see how to do it, so we talked to all the experts we could find, and none of them could say anything about this, had any ideas, until finally Francesco Maggi noticed that that inequality implies, just by looking at the derivative as q changes at one endpoint, this new sharp log Sobolev inequality, in which he's the expert. And he said, this thing, he said, yes. He said, I've never seen this before, but I know this is true, and I'll send you the proof. And then after a few weeks, he wrote to us and said, actually, I don't know how to prove this. So even that corollary was open for a little while, but luckily the students found it essentially in the literature. It follows from some results that were known before. And then they spoke, we have this summer meeting of the Mathematical Association of America. Lots of students go. It was at Wisconsin, Madison that year. And they spoke there. And this is Juan had worked on that a lot from Korea. And this is what he had to say about it.
We work on a log Sobolev inequality on a compact interval, which suggested by Francesco Maggi follows from a stronger inequality conjectured by 2009 geometry group. Despite its simplicity, the experts whom we contacted couldn't come up with a proof. We luckily found an equivalent result in a 1990 paper by Ducher and Stroop.
So so that did not settle the main conjecture, though. That just settled that corollary that Maggi had deduced if this were true. But it was evidence that this thing might be true. By the way, we have a great time with these students. We have about 40 of them at Williams every summer from around the world. And I have a group of 4 or 5. And I hope that maybe you guys will send us some for next summer. The applications are due in early February. Now, I've so far for them been just talking about positive powers of the distance from the origin, so that we have these increasing densities. If, on the other hand, you look at powers, say, very negative, less than -2, then the solution actually is a circle about the origin, although the enclosed area is on the exterior, not on the interior. Of course, there's infinitely much area on the interior, due to the fact that the density blows up there. And for intermediate densities, say r to the -1, the isoperimetric region doesn't exist. So you can actually do better and better by taking larger and larger annuli and actually have the limiting perimeter go to 0. So existence is often a problem when you're looking at the isoperimetric problem with density, and one of the organizers here is sort of the expert on this. So Aldo has done work with I've even worked with many different collaborators with good results on existence in certain cases. For example, for radial increasing densities. Well, in many of these examples, we've been disappointed that although the problem had rotational symmetry, the isoperimetric solution did not have rotational symmetry, was not a sphere or a ball centered at the origin. In the Gauss case, we realized that was because it went to 0 at infinity, and therefore the isoperimetric solution wanted to go out towards infinity. But even with something like r to the p, where it was growing, where it was going to infinity at infinity, it was not a circle about the origin, it was a circle through the origin, displaced a little bit. It turns out that if you want the circle about the origin or a sphere about the origin to be stable, you need the density to grow very rapidly. The exact condition is that you need the log of the density to be convex. That's the exact stability condition, which was first computed by Ken Bracke and led then to the conjecture that that necessary condition might also be sufficient. So this was the so-called log-convex density conjecture, that balls about the origin are isoperimetric in Rn if and only if the log of the radial density is convex, which is the stability condition. The same idea we talked about with the Granada students, stability implying minimization in these particular cases. Now so the big news on this was that this was proved. Paper was just published last month, I think, by Greg Chambers, an advanced graduate student at the University of Toronto. He's now at the University of Chicago. So I want to say something about the progress from that conjecture, 2004, to this proof, which was 12 years later. So there were certain examples that were known before. The easiest example is density e to the r squared. This was actually settled by Borel back in 1986. And in that case, you can prove it just using Steiner symmetrization. And the reason is that the density is a product, right? E to the r squared is equal to e to the x squared times e to the y squared. So you can use a symmetrization argument in that case. In fact, as I learned from Nicola, this is now sort of a very standard argument, although back in those days they used other proofs. They were a little worried about some of the technicalities. But that will only work for this example. The only rotationally symmetric function that's a product is e to a constant times r squared. That's it. So, and in fact, Steiner symmetrization never works in other cases. In fact, this was proved by the Napoli group, who are all here in great numbers today, right? I have one picture up there. I have Friedman's picture up there. Maybe we'll see where are they all here? It's a big contingent. So if you take even something like a spherical cap with density, say r to the 1.5, and apply Steiner symmetrization, you preserve volume, and the perimeter actually goes up. So there's no hope of using symmetrization in other cases. There were some results for large volumes. That turns out to be a much easier case. So that was first noticed in special case by Kolesnikov and Zanoff, and the most general, clear argument by Sean Howe, one of those students you met earlier, that if you have large volume for one of these uniformly log-convex densities, then the isoperimetric solution is a ball centered at the origin. And it was also known for small volumes. So this was work by Fagali and Maggi by asymptotic analysis. And that's good too, so we did small and large. That looks very good, but there's a long way between small and large. And neither of these methods seemed to indicate you could do the general result. The first method for large volumes was really an elementary argument, basically using the divergence theorem, or another way of thinking about it is you don't even have to worry about the whole area. Spheres even minimize the tangential area, even if you let the wobbling go for free. So that's a large volume, so it's sort of an easy case. This case has asymptotic analysis. Meanwhile, there were some other examples if you looked at just part of the whole space. So here's another result from the Napoli group, and this time the picture is from taking turns here, Francesco and Anna. So here the result was in an orthant with certain kinds of density. Here we have not only that exponential e to the r squared, that Borel factor, but there's also powers of the various coordinate functions there. It's still a spherical cap centered at the origin in cases like that. So there were a number of results like this, and so it was rather exciting when I heard an announcement coming from Spain of a very... Right. This is... Oh, I didn't show you their picture before, did I, when I told you it? There they are. Sorry. There they are. Oh, no, I don't know. Anyway, the proof here... Oh, it's just the proof. That's the new thing. The proof here is the idea of the proof is, in the plane, in the two-dimensional case, you just look at the equilibrium curves, and then you use induction to work your way up to higher dimensions. So there were a lot of ad hoc arguments like this. So it was kind of spectacular then in 2013 when I heard about this very general result. So this very general result that says, in any convex cone with any density that just has this property, for any positive k, the kth root of the density is homogeneous and concave. Those are the hypotheses. Very general, and tons of examples, including many of these that had come before. In that case, the spheres about the origin are isoperimetric. So this looked very general, and so we were very eager to see what kind of a proof it had. Now, the favorite method for proving isoperimetric problems had been some kind of a mapping argument, that lets you compare a candidate with the sphere that you're trying to, so you have some correspondence between the two so that you can do a comparison just by a mapping argument. And this proof, which I learned about at a meeting in Barcelona where I met Cabre and his graduate students, who were the first ones to prove it, used a kind of mapping comparison. Now, there were many of these around. I was familiar. Maybe you've known probably the most famous one is this one that's due to Gromov. He attributes Canute for the idea, and Brachy pointed out that it works in parts of in cones, in convex cones, as well as in the whole space, where you do a certain mapping vertical lines to vertical lines and preserving volume, something like that. It's not entirely satisfactory, and it's very ad hoc. It depends on the coordinate system. So it's not a very natural mapping. And so people wanted to look for a more natural mapping, and you would look to optimal transportation, probably. And there also was an optimal transportation proof. You met Robert McCann before, due to McCann and Trudinger. And the thing is, when you take optimal transportation for carrying all this mass on the left, all the mass on the right, a minimizer exists by the theory, and it's always a gradient. So this is additional information that helps in the proof. And the key ingredient in the proof is the divergence theorem, where you take the divergence of that gradient, which gives you the Laplacian, and then by the divergence theorem, that's equal to a certain integral over the boundary and lets you do the comparisons. Now, there was a third approach due to Cabre, a third mapping idea that I didn't even know about. But what Cabre said was, since the Laplacian is so important in these proofs, let's use a map, the gradient of some function u, where the Laplacian is constant. That should make it easier. So that was his idea, to take the Laplacian constant. Don't have all the details written down here. It's a little problem. To take the Laplacian constant. And this gave a different kind of mapping argument. Now, none of these mapping arguments seem to work when you have density around. So things look sort of hopeless. Mapping arguments don't work. The extraordinary thing was that Cabre and his students discovered that this mapping you can generalize to work with density. So generalize to work with density. So now instead of setting the Laplacian equal to a constant, the right constant is the perimeter of the candidate, the competitor, you set the so-called weighted Laplacian or drift Laplacian equal to a constant, which has the density factor appearing in it a couple of times. You do that. And then what was a simple argument before goes through, although it gets much more complicated. I put some of the headlines here just to give you a sense that it does get very complicated. Although it goes on for pages, it's kind of a miracle that it works. And it makes you wonder how they ever could have found it. And so I asked them about that. There are the three of them. Cabre, who first found this mapping argument in the classical case, and his two graduate students who found that it generalized. I asked them about it. This is what they had to say.
Around 2000, I proved the classical isoperimetric inequality in Rn with constant density using a gradient map produced as the gradient of a function which solves a linear Neumann problem for the Laplacian.
Some years later, we work in a PDE problem, and we get involved in Sobolev and isoperimetric inequalities with monomial densities. After some tries of proving it, we succeed to adapt the proof of Cabre to these monomial densities.
And then, having this intuition of the monomial densities that helped a lot, we started to see what other ways could work. And we had this, we found this class of weights that satisfy this concavity condition in cones. We were surprised.
We were surprised, he says at the end. I like that. We were surprised. Yeah, it was a miracle that it worked. So there was great excitement about this. All these new ideas for proving the log-convex density conjecture. So that was one, the new mapping argument. There were two other proofs that came out at about the same time. The Granada group, the Rosales and Cañete, had a proof using stability analysis, which actually proves something more in many cases, that the only stable, smooth competitors were the spheres centered at the origin. And then there was an extremely elegant argument by Millman and Rotem in Israel using the Borel-Braskamp-Lieb inequality, which is a generalization of Brun-Minkowski, which is considered a favorite way to prove isoperimetric inequalities for density 1, and the generalization of Brun-Minkowski to other densities is this so-called Borel-Braskamp-Lieb, and we're lucky enough that we'll hear more about that later in the conference. Paulo is talking about that on Thursday at this new time, right, 4 o'clock. Where's Paulo? Is here, right there. So you'll hear a little more about Borel-Braskamp-Lieb on Friday. So there were all these new ideas, much hope for log-convex density conjecture proof. None of them helped in the least. It turned out that the cases that they covered were much easier than the general case. The kinds of cases that you can prove using the divergence theorem, that work for large volumes, that kind of stuff, not the nitty-gritty difficulties of log-convex density conjecture. And it was just this year, I think last month, when this proof by Greg Chambers was published, proving the result, not using any fancy, deep new ideas, but doing it sort of in the most intelligent way that you would do it, the simple, direct way, even though it was kind of messy. So I just want to tell you a little bit about how his proof goes, that all of these balls, if you have one of these log-convex densities for which the balls about the origin are stable, then those balls are minimizing. Solve the isoperimetric problem. Now, all these arguments start with a certain symmetrization that you can do, called spherical symmetrization. The green blob there has already undergone spherical symmetrization because, as you can see, any purple sphere intersects it in a spherical cap centered on the x-axis. And that's the result of spherical symmetrization. Maintaining volume and reducing perimeter. And that green blob that you get as a result is now a surface of revolution around the x-axis, so it's completely determined by its generating curve in the plane. So it's really a question about curves in the plane. And so in analyzing what this curve might look like, Chambers starts at its point farthest from the origin. And now if it doesn't stay at that distance from the origin and be a circle about the origin, it must start curving inward, so it must have greater curvature here, start curving inward, and he was able to show by analyzing the differential equation that such a curve would have to satisfy for equilibrium that it would spiral inward instead of closing up in any reasonable way, and he got a contradiction like that. But it was not an easy comparison to make. It wasn't like the curvature increased monotonically. No, he had to choose corresponding points on the curve and make point-wise comparisons. The estimates were very delicate. It took some 44 pages of careful analysis. And this is often how you really solve these kinds of problems, right? By getting your hands dirty with the differential equation and hard estimates and not some abstract arguments. So that is what worked for Chambers. This is I was on a hike around Williamstown in the Berkshire Mountains with Chambers, and I asked him if he wanted to say anything about working on this, and this is what Chambers had to say.
So the proof of the log-convex density conjecture first involves reducing the problem down to axially symmetric minimizers, and then examining the generating curve. So from a first-order formula, you can produce an ODE for this curve, and you can show that if it's not an upper half circle, it has to spiral in too quickly. But what's fascinating is that the estimates involved in proving this are actually very delicate, surprisingly delicate.
Yes, well said. So that's proved in Euclidean space. You could ask, here's a similar conjecture, does the same result hold in hyperbolic space? Again, the stability condition is that the log of the density is convex. This is an open question. I actually had my students working on this past summer, and they got a result in that direction with different volume and perimeter densities. Sometimes you're allowed to do that. The volume density was anything that was log convex, but the perimeter density had an additional factor of cosh squared thrown in to help their proof along. The leader in doing that, it was a comparison argument. The leader in doing that was Leo de Giosa, and here's what he had to say about working on it.
In 2015, Greg Chambers provided a proof of the log-convex density conjecture. We provide a partial extension to hyperbolic space, in which perimeter and volume densities are related, but different.
Then just this June, there have been lots of people looking at different perimeter and volume densities. These come up a lot, but the best of these conjectures appeared on the archive just in this June, again by the Napoli group, we're coming to love here, about the simplest densities you could have for perimeter and volume, that is both powers of R, but different powers. So perimeter volume density R to the M, perimeter density R to the K, and the stability condition involves M, K, and the ambient dimension N, but it's very easy to write down the stability condition. And the conjecture is that that's sufficient for balls to be minimizing. And this actually came up because of applications to partial differential to differential equations and weighted singular Sobolev inequalities, in particular Caffarelli-Cohn-Nuremberg inequalities and Hardy inequalities with applications to eigenvalues and nonlinear and degenerate partial differential equations. This actually implied some earlier conjectures due to Cadaroli and Mussina. This was a great conjecture, I thought. It was a great conjecture on the archive in June, and then it had been proved if you put a stronger condition on M over K to take it to the easy region where the divergence theorem worked. That's again backed by Sean Howe, whom I mentioned earlier, one of the Granada students. And then this summer, my students actually proved that conjecture. So that conjecture is true for these different densities, powers of R. Stable implies minimizing. Stable implies minimizing. And the proof was the same as the Chambers proof. They went through and redid the whole Chambers proof lemma by lemma in this different scenario where you have different perimeter and volume densities, and everything went through. And in fact, another one of the corollaries was this analytic conjecture that I mentioned earlier, this very strange analytic conjecture, that also follows from this result. So that was a lot of interesting news. And the lead on this project was Leah Königsberg, and this is what she had to say.
In 2015, Chambers provided a proof of the log-convex density conjecture in Rn. We extend this result to some cases where the perimeter and volume densities are different. And then also you remember this conjecture, the conjecture that spheres through the origin are minimizing when the powers are equal. Now notice back here, M is always less than K when you get balls centered at the origin. When the powers are equal, the conjecture was that you get a sphere through the origin, And that was proved by the students last summer. And with some help, Chambers came to visit and consulted with them for a while, and they had a joint paper in the end. But that was considerably harder than Chambers' proof. There were actually two hard cases, other technical complexities. The one case was like Chambers. So again, you start at the place where the farthest from the origin, and if you're not the sphere through the origin, you might have greater curvature. In that case, you spiral inward, and they got the contradiction that you don't really have spherical symmetrization anymore, because you can see that purple sphere intersects that competitor there in two spherical caps, not centered on the x-axis. But the harder case, now there's the case, since you're only comparing with a circle through the origin, you can actually curve less than that and still start farthest from the origin. But in that case, again, you get a different kind of failure where the intersection with this purple sphere, again, is two spherical caps instead of one. And that was the harder case to do. So this is what Sarah, who led that effort, had to say about it.
To solve the isoperimetric problem in Rn with density R to the p, We show that the solution to an equivalent isoperimetric problem in the plane is a circle through the origin. We use a proof by contradiction in two cases. In both cases, we compare curvatures at opposite points of the same height. In one case, the curve spirals in, and in the other, it has a pointy teardrop shape.
Yes, good. So now what would be the most general conjecture about spheres centered at the origin? Maybe something like this. Spheres about the origin are isoperimetric, and now we're going to allow densities and metrics to change, and hope that stability implies minimization. That would be the most general you could have. That's not true. It's been known for some time that sometimes in situations like this, even in surfaces of revolution, you can get an annulus bounded by two such circles about the origin. So maybe then you would want to assume that, so then maybe a second version would be that isoperimetric regions are rotationally symmetric and bounded by spheres and circles about the origin. But it turns out, I just realized last month, that that's false too. So here's a counterexample. This is just density 1. This is a surface of revolution where all the circles about the North Pole are stable, but little ones are not minimizing because it's possible to have the Gauss curvature larger down here and small circles want to be about the point of maximum Gauss curvature. This is hard to do because the stability condition, something less than 1, has the same increases and decreases with the Gauss curvature. So you start out with the value of the Gauss curvature, and Q starts out being 1. You have to keep Q less than 1, but you want to make G bigger. It seems impossible until you realize there's that F squared factor there. So if you first decrease where F is big and then increase where F is small, you can end up with G bigger and Q smaller and get this contradiction so that small isoperimetric regions are just circles down here and not circles about the origin. So that's not true. Here's the best conjecture that might be true. Spheres stable implies that spheres are minimizing among graphs over the unit sphere. So that's the best conjecture we could have now, and that's actually been proved for unit densities, that is for the classical case, in a paper that just appeared on the archive. So maybe that'll be true after all. If you want to hear more about densities, I have in the new edition of my geometric measure theory book, there's a chapter about that. I hope you like them as I do. Thank you very much.